Welcome to the Bodhi Academy. My name is Amisha Classo, and in today's video we will talk about the chapter Thermodynamics, class 11, chapter 5. So today we are going to discuss some of the last concepts of this chapter. Okay, mainly the laws of thermodynamics are what we are going to discuss in this part of the video. Now, spontaneity. So the first law of thermodynamics tells us about the relation between heat absorbed and the work performed on or by a system. So here we are talking about a relation, that is internal energy equals to Q plus W, where we are relating all the terms, that is energy, to the work done and also to the heat that is being absorbed. So now it puts no restrictions on the direction of heat flow. However, the flow of heat is unidirectional from higher temperature to lower temperature. In fact, all naturally occurring processes, whether chemical or physical, will tend to proceed simultaneously in one direction only. For example, a gas expanding to fill the available volume, burning carbon in dioxygen, giving carbon dioxide. So now what we are saying is that when we talk about heat flow, okay, any heat flow that occurs, it always occurs from a region where there is a higher temperature to a lower temperature. So it is unidirectional, okay, it will only proceed in one direction. So it is very common that heat is always proceeding in either of the one directions, okay, it won't go simultaneously in both the directions. Now, but heat will not flow from a colder body to a warmer body on its own. The gas in a container will not spontaneously contract into one corner, or carbon dioxide will not form carbon and dioxygen spontaneously. So now what we are saying is that when we want to reverse this formula, okay, when we want to make the flow occur from a colder body to a warmer body, which usually doesn't happen, so it won't occur by itself, correct, we have to give it some source of energy so that it moves or it proceeds in that way. Now we may ask, what is the driving force of spontaneously occurring changes? So now if say we are saying some reactions are spontaneous, then how come are they spontaneous? What is the force that drives them to be spontaneous? What determines the direction of the spontaneous change? Okay, in this section we will establish some criterion for these processes, whether these will take place or not. Now let us first understand what do you mean by a spontaneous reaction or change. Okay, so you may think by your common observation that spontaneous reaction is the one which occurs immediately when contact is made between two reactants. Okay, so if I say I take up a container, okay, which is filled with two reactants maybe, okay, and I mix them. So what I'm expecting is that it will occur spontaneously by itself, not me, I'm not applying any source of outer power or energy, nothing, they are just going to react by themselves. That is an example of a spontaneous reaction. Now let's take an example of combination of hydrogen and oxygen. Okay, so these gases may be mixed at room temperature and left for many years without observing any perceptible change. So now if you take hydrogen and oxygen and you mix them at room temperature, okay, what you are going to see is that the reaction will occur, but it won't be visible to our eyes nakedly. Okay, we won't be able to see any external change that is occurring. Now although the reaction is taking place between them, it is at an extremely slow rate. So even though the reaction is occurring, it is at such a slower rate that we are not able to see any physical change that is happening. It is still called spontaneous reaction. So as to why, the minute we mixed hydrogen and oxygen, the reaction had already begun. So it is a spontaneous reaction. So spontaneity means having the potential to proceed without the assistance of an external agency. So whenever a reaction proceeds by itself without outsourcing any other external assistance or any other external source of energy, that is known as the spontaneous reaction or the spontaneity of that reaction. However, it does not tell about the rate of a reaction or process. So here we have a limitation, that it does not speak about how fast the reaction is, how slow it is, in how many steps it is taking place. We have no control over that. Okay, so that is one limitation. Another aspect of spontaneous reaction or processes, as we see, is that this cannot reverse their direction on their own. So this is what we spoke about, right? It is unidirectional. It will go in only one direction. Until and unless you are making it forcefully change its direction, only in that case it will change its direction. Otherwise, apart from that, it will continue to move forward only in the particular one direction. So we may now summarize it as follows. So a spontaneous process is an irreversible process and may only be reversed by some external agency. So it is an irreversible process by when it occurs by itself. If you want to reverse it, you have to apply some kind of external agency or external energy. Now, is decrease in enthalpy a criteria for spontaneity? Now we are going to relate enthalpy with respect to spontaneity. So if we examine the phenomena like flow of water downhill or fall of a stone onto the ground, we find that there is a net decrease in the potential energy in the direction of change. By analogy, we may be tempted to state that a chemical reaction is spontaneous in a given direction because the decrease in energy has taken place, as in case of exothermic reactions. So if you see here, what you see is that the enthalpy keeps on decreasing. So the decrease in enthalpy in passing from the reactants to the products may be shown for any exothermic reaction on an enthalpy diagram. Thus, the postulate that driving force of a chemical reaction may be due to decrease in energy sounds reasonable. So, the driving force that we were questioning? We question that what is that driving force of spontaneously occurring changes. So, we can say that it is due to the decrease in energy that occurs. Okay, and that is maybe the reason that it forces that itself acts as the driving force of spontaneously occurring changes. Okay, next let's look at this entropy and spontaneity. Now we are talking about a new term, that is entropy. All this while we were talking about enthalpy, now we will learn about entropy. So then, what drives the spontaneous process in a given direction? Let us examine such a case in delta H equals to 0, that is enthalpy is 0. So there is no change in enthalpy, but we are saying still the process is spontaneous. How is it spontaneous? So now let us consider diffusion of two gases into each other in a closed container which is isolated from the surroundings. Okay, say we have these two containers. Okay, now what we are doing here is that, say in one side we have reactant atoms or reactant molecules of gas A, and here we have gas B molecules. Okay, and here we have a movable membrane over here. Now what will happen if you remove this membrane? Obviously there will be some kind of mixing that will happen. Both of them will evenly mix out throughout. Okay, now when we had this image, okay, now if I dive my hand into the left side of this where we have reactant, where we have these A molecules, I will be very sure that the minute I pick out a molecule, it is going to be a molecule. Okay, same way if I drive my hand into the other side of it and try to pick out a molecule, I know I will get a molecule of B gas. Okay, but when I look at this situation here where everyone is evenly distributed mixed thoroughly, okay, here no matter where I put my hand, I am unsure or I am uncertain about what am I going to pick out. Am I going to pick out a molecule A or molecule B? So what are we saying here is that this is highly ordered, okay, whereas this is highly disordered, or there is high amount of randomness that is created over here. In this, we are precisely having only molecules of reactant A, and here we have only molecules of reactant B. If you see here, we have uncertainty, we have a disorder or randomness of all of them being randomly arranged at any point or at any corner. So we may say that here there is always a tendency. In an isolated system, we can say that there is always a tendency for a system's energy to become more disordered or chaotic, and this could be a criterion for spontaneous change. So here we have defined a new terminology or a new concept that occurs of disorder or randomness. Okay, so now what is this disorder or the randomness that is present? Now at this point we introduce another thermodynamic function known as the entropy, that is denoted by the alphabet S. So the above mentioned disorder is the manifestation of entropy. So to form a mental picture, one can think of entropy as the measure of degree of randomness or disorder in the system. So entropy is basically how randomly these molecules are arranged or how much level of disorder is present in this system. Now, the greater the disorder in an isolated system, higher is the entropy. So, more mixed or more uneven is the solution, we can say higher is going to be its entropy. Now, for a given substance, we need to always remember that, see, we have a crystalline solid. Crystalline solid as in they are high in they are highly ordered and they will have therefore the lowest entropy, because we are preferred entropy tells us about more of the randomness, more of the unevenly order that is present. Here in crystalline solids, we know that they are highly ordered. Each of the atom molecule is placed correctly right into their position. So here we are going to see very low entropy. But if you look at gases which are present, correct, gases, they are randomly arranged. So in that case, what we can say is that it will have a very higher entropy. Now if we want to quantify this entropy, we have two major ways to do this. First is to calculate the degree of disorder or the chaotic distribution of energy among molecules through statistical method. But this is beyond like what we can basically do for day-to-day need. So another way is to relate this process to the heat that is evolved in the process, which would make entropy a thermodynamic concept. So other way we are saying is that we could consider entropy as the measure of heat it is that is being involved or it is being released in this concept. Now whenever heat is added to the system, it increases molecular motions, causing increased randomness in the system. Thus heat, that is Q, has randomizing influence. Now what we can say here is that we know on increasing the heat of a substance, what we are doing, we are increasing its kinetic energy. The molecules or the atoms which are there, they are going to move more faster, and therefore the randomness of the system will increase. Thus we can say that heat is known as to have as a randomizing influence, as in it is influencing it to be more random. A system at higher temperature has greater randomness in it than at a lower temperature. Thus temperature becomes the measure of average chaotic motion of particles in the system. Now, if this suggests that the entropy change is inversely proportional to the temperature, we can relate delta S to Q and T for a reversible reaction in this manner, where we have delta S equals to Q reversible upon T. Now, the total entropy change, that is S total, for the system and surrounding of a spontaneous process can be given by delta S total equals to delta S of the system plus delta S of the surrounding, which is less than 0. So when a system is in equilibrium, the entropy is maximum and the change in entropy delta S becomes 0. So now we can say that the entropy for a system process increases till it reaches its maximum capacity, and at equilibrium the change in entropy will remain to 0 itself. Now what we find here is that for reversible and irreversible expansion of ideal gases under isothermal conditions, we know that delta U goes to 0, but here delta S, that is a combination of delta S of system plus surrounding, it is not equal to 0 for irreversible processes. Thus delta U does not discriminate between reversible and irreversible processes, whereas delta S does. Next we have something about Gibbs energy and spontaneity. Now we have seen that for a system it is the total entropy change, that is delta S, which decides the spontaneity of the process. But most of the chemical reactions, they fall in the category of either closed or open system. We don't usually work into isolated systems. So therefore, for most of the chemical reactions, there are changes in both enthalpy as well as the entropy that occurs. So it is clear from the discussion in the previous sections that neither decrease in enthalpy nor increase in entropy alone can determine whether the direction of a spontaneous change for these systems. So for this purpose, we define a new thermodynamic function, the Gibbs energy or the Gibbs function, that is delta G or G, which is given as the difference between H, that is the enthalpy, minus Ts, that is the product of temperature and entropy. So here here G that is there, it is given as an extensive property and it is a state function. So the change in Gibbs free energy for the system, that is delta G, can be written as delta G system equals to delta H system minus T delta S minus S system delta T. So at constant temperature, delta T will be equal to 0. So if we consider this to be 0 at constant temperature. So usually the subscript system is dropped and we simply write the equation as delta G equals to delta H minus T delta S, where we are saying Gibbs energy change is equal to the enthalpy change minus the temperature into the entropy change, and this is referred to as the Gibbs equation, and this is the most important equation that is known in chemistry. Now for here we have to consider both the terms together for spontaneity, that is the energy in terms of delta H, and entropy, that is a measure of the disorder as indicated earlier. Now let us consider now delta G is related to the reaction spontaneity. So we know that delta S total equals to delta S system plus delta S surrounding. So if the system is in thermal equilibrium with the surrounding, then the temperature of the surrounding is same as that of the system. Also, increase in enthalpy of the surrounding is equal to decrease in enthalpy of the system. Therefore, the entropy change of surroundings, that is delta S surrounding, will be equal to delta H surrounding upon T will be equal to minus delta H system upon T. So if on rearranging we get the equation that delta Ts total equals to T delta S system minus delta H system. So for spontaneous reaction we can say delta S total, which is there, it will be less than 0. So here we get this final equation, that is delta G equals to delta H plus T delta S being greater than 0. So for delta Hs is the enthalpy change of reaction, delta Ts is the energy which is not available to do useful work. So delta G is the net energy available that can do any kind of work and is therefore known as the measure of the free energy. For this reason, it is also known as the free energy of the reaction. Now delta G, depending on the sign convention, or we can say depending on the sign convention, we can call it as spontaneous or non-spontaneous. If delta G is negative, that is greater than 0, we call it a spontaneous reaction. If it is positive, that is less than 0, it is known as the non-spontaneous reactions. Next we have entropy and the second law of thermodynamics. Now the second law of thermodynamics explains why spontaneous exothermic reactions are so common. Firstly, we talked about spontaneous reactions. Now we are focusing on why are they mostly common only as exothermic reactions. Now in an exothermic reaction, heat that is released by the reaction increases the disorder of the surroundings and the overall entropy change is positive, which makes the reaction spontaneous. So what we are saying, we already spoke how heat has an effect on the entropy. More the amount of heat, more the temperature you rise, more is going to be its entropy, and similar thing also works on to the surroundings of the same. and therefore the overall change over here that occurs tends to be a positive change, and therefore it makes the reaction a spontaneous reaction. Now, absolute entropy and the third law of thermodynamics. So these, now if you know, when you apply some kind of heat, the bonds are going to always, either they are going to move in a straight line, or they are going to vibrate, they are going to rotate, there will be some kind of movement. Now these motions which occur of the molecule are called translational, rotational and vibrational motions respectively. Now when the temperature of the system rises, these motions which are there, they become more vigorous and the entropy increases. On the other hand, when temperature is lower, the entropy is going to decrease. So what we can conclude is that the entropy of any pure crystalline substance approaches zero as the temperature approaches absolute zero. So we are saying that the crystalline substance, it will tend to come to zero, so that when the temperature also comes to zero. Now this is known as the third law of thermodynamics. Next we will talk about Gibbs energy change and equilibrium. So now, knowing about all of these things, we were able to make two basic two basic things we were very sure about is what? Prediction of spontaneity of the chemical reaction and prediction of useful work that could be extracted from it. First we define how we can tell if the reaction is spontaneous or no. Secondly, using Gibbs free energy, we were able to define the useful work, that is the energy that can do this useful work, that is the free energy that is available. So reversible under strict thermodynamic sense is a special way of carrying out a process such that the system is at all times in perfect equilibrium with its surrounding. When applied to a chemical reaction, the term reversible indicates that a given reaction can proceed in either direction simultaneously, so that a dynamic equilibrium is set up. This means that the reaction in both the directions should proceed with a decrease in free energy, which seems impossible. It is possible only if at equilibrium the free energy of the system is minimum. If it is not, then the system would spontaneously change to configuration of lower free energy. So the criteria for equilibrium that we know is that A plus B should give us C plus T, and it should be a reversible reaction. Now if we are saying delta G equals to 0, that is Gibbs free energy for a reaction in which all the reactants and products are in their standard state, delta G naught is related to the equilibrium constant of the reaction as follows. So we are saying this whole equation we equate it to 0. In that case, what we can do, we shift this and we get minus RT ln K. We remove this ln and we add minus 2.30 T RT log K. So we also know that delta G naught will be equal to delta H naught minus T delta S naught. That overall it equals to minus RT ln K. So for strong endothermic reactions, the value of delta H naught may be large and it may also be positive. But in such cases, value of K will be much smaller than 1 and the reaction is more likely to form much product. In case of exothermic reactions, delta RH naught is large and negative, and delta G naught is likely to be large and negative too. In such cases, K will be much larger than 1. We may expect strongly exothermic reactions to have large K values, and hence it can go to near completion. Delta RG naught also depends upon delta RS naught. If it changes in entropy of a reaction is also taken into account, the value of K or extent of chemical reaction will also be affected depending upon whether delta RS naught is positive or negative. So it is possible for us to do two things now, that to obtain estimate of delta G naught from the measurement of delta H naught and delta S naught, and from that we can calculate K at any temperature. Then if K is measured directly in the laboratory, we can directly find the values of delta G naught at any temperature to be found. So that was it for this whole chapter of thermodynamics. I hope you have understood. Please don't forget to like, share and subscribe to the Bodhi Academy.